Okay, so I've had some requests to make a data reduction video for the 5th lab. So for that one I had all of you do that on your own. I give you a recommended guide if you wanted it, but I wanted you to do it on your own. But again, I've had some requests to make a video for how to go about it, or at least how I went about it. So I think the hardest thing for this lab, for that data reduction, was either the nested for loop or actually finding that ductile to brittle transition temperature. So let's take a look at what we had to do. We needed to make 2 different graphs, and on these 2 graphs we had the 3 different curves for aluminum, steel, 1018 steel, and then 4140 steel. Right? Then we had our fracture images. There's no sample calcs here. And yeah, so here's the guide. So basically what we're going to do today is go through this kind of recommended guide that I had. So the first thing we'll do is use a for loop to import both of the Excel sheets. And we've done this on, I think, pretty much almost every lab now. We've used a for loop where we did at least very similar code to import the data. And then we're going to use a nested for loop, which we haven't done so far this semester. So this will be the first time. To loop through each of the different materials that we have within each sheet. So you don't need to use a nested for loop. I think it's easiest with how all of the data is kind of structured this time around. But if you didn't want to use one, you don't have to, especially because it might be kind of digging into the past, I don't know, like a few years ago when you took the MATLAB class. Okay, so we're going to loop through for that, and then we're going to solve for the transition impact energy. So for that, E, that means energy. So that transition energy is going to be Emax, so the maximum impact energy that we had, plus the minimum impact energy that we had, divided by 2. Okay, then we get that. So basically that'll be a horizontal line on our graph. And what we want to do is once we get that horizontal line, once we find that, we want to find the intersection point when it intersects with those curves that we made. And we want to draw a line down from that, a vertical line down. And that's going to correspond to that ductile to brittle transition temperature. Right, so that's why we need to first, take this impact energy that we solved for, and then we want to convert that into a vector. So we need to convert it to a vector so we can actually basically have a plot. We need at least 2 values to plot a line. So if you have a vector of at least 2 values in there, then we can have it. So this vector, it's going to be a vector where every single element within that vector is going to be the exact same number. So let's say our transition energy was 30 degrees Fahrenheit, just totally random. Then we would want a vector of at least 2 values, that is 30 and 30. And then we can make that line, find that intersection point with the curve, and then find the transition temperature. So we use the vector here, or we make the vector here, and I'm going to make this vector by using polyval. And again, you don't have to use that. That's just what I did. And then to find our intersection point, we use polyx, poly-y, which we did in, I think, the very first lab. And then we get our transition temperature because the transition temperature is going to be the x-intercept value for the intersection point that we get. And then we can make our plots. And so we're not... you didn't have to plot the transition temperature in your graphs. I did for, I think I showed some of you in Discord a graph with that transition temperature in there. So we'll do that as well in this video. Alright, so let's go back here. I did some very basic stuff like I usually do. So here's our data. I had it for, all of the labs that I'm teaching this semester. So the one we're going to use, I guess, right now is Friday at 11:30. And then I made a string array for our title. So we're going to have 2 graphs in the end, and one of them is going to be for the left station, and one is for the right station. Why don't I just go to the graphs that we're going to make. Pardon my French there. Where did I put them? Oh, it was probably in here. Yes. Okay, so here are the graphs that we're going to make today, I think. I forget if my script here has both of these lines, but I don't know. We'll get to it. So this kind of thicker dashed line here, that's the energy transition temperature that I talked about. And then the smaller dashed line here, that is the transition temperature. So energy transition here, transition temperature here. And then we can see, if we're looking at this line here, for this energy transition, you see that once it crosses this red line here, basically we want to find the intersection point, which is obviously right here. And that x-intercept value, if we draw a line down, this is our transition temperature for, in this case, 4140 steel. My colors look kind of weird here, but yeah, that's what it is. Alright. So first thing we're going to do is loop to import all of our data. Oh yeah, let me make my text bigger. Should be plenty. And okay, so we're going to do for n equals 1 to 2. So right now we're just going to import the different sheets that we have. Okay. Alright. Okay, so I'm going to call this data equals read matrix like we usually do. File name, that's telling us, where our file is stored at. Okay, file name, then we're going to call out our sheets, and we want to loop through sheets 1 and 2, so we're going to put n, and the range that we want, for me, and I think for all of you actually, it should be B2 to G7. You may have had to change that, I don't know. Let's go back to the Excel file, so we gotta go to data, Friday 11:30. Okay, here we go. So that was what, B2, so that's right here, all the way to G7 right here. And that's the same for each sheet that I have here, B2 to G7. And yeah, you got to make sure both of these sheets are formatted the same. Alright, so there we go. So if we run this now, we can import our data. If we open that up, then you see everything right here. Because we're looping through, this is for the very last iteration or last pass in the loop. So what I did is I made a few vectors, one for temperature and one for the impact energy. So it was easier for me later on to kind of use that in my code. Again, you don't have to do this part. For me, I did it just because it was simple. So I'm going to say temperature. I'm going to get all of that temperature data. So I need to use array addressing. So we'll say data. I want to get all of the rows. And here, if you had me for MATLAB, yes, this is hard coding. But it's okay. So if I open this up now, then this is all of the temperature values that I have. Okay, cool. So let's go back here and basically see that, yeah, if we go back here and we look at all of the temperature values, that's what we just extracted. Again, I don't have to do that. I could do all of this on a different line later on, but I'm just keeping it kind of straightforward, easy to keep track of everything. And let's do it again for our impact energy this time. So impact energy, what did I call this? Just energy, okay. Energy, that's going to be equal to data. And again, we want all of the rows. And this time we want columns 2, 4, and 6. And now let's open this up, open energy. And there we go. We have all of our impact energy. So, let's see. Okay. I was taking a look at these numbers here. And now we are going to go into the nested for loop. So we'll do nested loop for materials. And for this, we're going to do for I equals 1 to 3 because we have 3 different materials in each of the sheets. Let's actually call this transition energy. Okay, so this is going to be solving for that transition energy that we have. And remember, that was Emax plus Emin divided by 2. So let's call this dBTT underscore energy. And this is going to be equal to the maximum energy that we have. You know, I'll first do, now let's do it like this. So we'll do max energy, and this is all I'm gonna write for right now. So basically I'm gonna show you, you know, kind of what we want to get. It's the maximum energy per material per sheet. So let's reorganize this a bit. Let's run this, okay? And here we go. So over here, if we go to our data sheet, actually let's go to temperature. This is for the very last pass that we have, so this is basically sheet 2. And now we have our 3 different materials, right? So we want to see the maximum energy per material. So if I look at this value here, we see 142. And okay, this is for temperature. Where's 142? Oh, this is energy. I'm thinking about temperature. So let's go to energy here. Okay, 142, there we go. That's the maximum energy that we have for our first material, which is, I don't know, what was it? I forget. Our first material was 1018 steel. Okay. And then our second one, if we look at that column, we see that the max one is 45.5, and that was for 4140 steel, right? Yep. And then the last one we have is 14.5, which is right there, and that was for aluminum. So, you know, I put this I here because we want to look at this by material. So if I don't have this I, let's comment that out. If I like just had max energy, then we get it like this. So we basically get these vectors as an output, and that's not what we want because we want to loop through by material. Okay, so that's why I'm looping here with an I here for the column. So this is saying, look at all of the rows in the ith column. So basically look at all of the rows for 1018 steel, and then for 4140 steel, and then aluminum 6060, I think it was. And of course we're using the max function as well, because we want to get the maximum energy. If I take that part out, and these 3 columns here, it's just this, right? Here's our first column, that's what we got here. Second column, that's what we see here. And the third column, that's what we see here. So when you're kind of working on this stuff and you get stuck, you know, I think this line of code, especially because we put a comma I, we haven't done this kind of, I guess, array addressing. We haven't done that too often in this class, but if you kind of break things down, you know, really, really simple at first, just to kind of verify, you know, I guess, the very basics. You know, here we're just getting, you know, we're just getting this table really right here for the energy, but we're separating it by each column. So if you kind of break things down really simple, that's a good way to kind of debug or just kind of progress with your code. Okay, so anyways, let's go back here and let's actually do what we want to do, which is finding that transition energy per material per sheet. So we're going to type in max. Actually, I'm going to first have parentheses because I need our numerator wrapped in parentheses. So let's do max energy, and then again all of the rows in the ith column. We have 2 parentheses there, yep. Plus the minimum energy in all of the columns, and then it's going to be divided by 2. Okay, let's run this. So I should have 6 values here. Okay, so this is for our first sheet for 1018 steel, first sheet 4140 steel, first sheet aluminum, first sheet 1018 steel, first sheet 4140, first sheet aluminum, or sorry, second sheet. I think I was saying first sheet. Okay, so we have it broken up, you know, 3 values for the first sheet, 3 values for the second sheet. Okay, so now we are going to make a vector from that transition energy that we just solved for, so we can have that kind of plotted line, and then we can find the intersection with that plotted line with the curves that we already plotted. Okay, let's go up here. So I'm going to call this dbtdt energy vec, and I'm going to use the polyval function. And, you know, if ever, you know, there's some function that, I don't know, I tell you to use or someone else does, or you just want to, of course, just understand a function better, you can type in doc, and then polyval or whatever the function is, in the command window, press enter, and then you get the documentation that comes up. So the very first argument that we have is going to be p. That's just a placeholder variable, and that's going to be the polynomial that we're going to evaluate. So in this case, that's going to be our dBTT energy value that we solved for. And the second value is x, and then let's see, and x is going to be basically like how we evaluate our polynomial. So in a sense, it's basically what the length is going to be for the polynomial that we have. So remember, I said that it needs to be at least a length of 2. So I could just do, polyval dBTT energy, and then I can do something like zeros, 1 comma 2. So that's going to be a vector of zeros that has 1 row and 2 columns. So if I run this now, and here we go, we have a vector of a length of 2 for all of our dBTT energy values that we just previously found. And so we can leave it like this, and this is perfectly fine. So we'll be able to make this kind of graph, because we have those 2 points, we can make a plot now that's a horizontal line. So you know what, I'll actually just leave it like this. But what you could have done is, let's actually copy this and paste it. So what I did before is I did temp all of the rows in the ith column, and that's going to be basically a vector of 6 values. Let's unsuppress it, and that's what you see here. So in this case, it's a column vector of 6 values. Okay, I'll just use this one. But either way, each method works. We just need a vector of at least 2 values. Okay, now we need to find the intersection points. So again, that's the horizontal line that we just made. So that dBTT energy vec. So we're going to find the intersection for that, and or the intersection point for that with the curves that we are going to graph. So let's actually go back to that figure just to visualize it again. Okay, so it's this figure here. So what we just made, that vector is this dash line, and this dash line, this dash line, this one, and this one. Okay, that's what we just found. And even though we didn't make a plot, we have the data for these 3 curves here, because that's just the data that we collected. That's the impact energy and the temperature. So we have everything that we need to find the intersection points. I shouldn't have closed out of it. I should have hit it. Anyways, let's type in xint, yint. This needs to be the format that we you need this format for the polyx, poly y function. So polyx, poly y. And we are going to run this. Let's actually do the same thing, just like with polyval. Let's type in doc polyx, poly y. Okay, and here you go. So you can see the format that we need. We basically need one vector here of our x values and our y values. And then we need the x values and y values for our second vector. Okay, so that's simple enough. So for our first vector, the x values, that's going to be dBTT. Sorry, not that. It's going to be temp. Take that out. Okay, temp. All of the rows in the ith column. So we have our temperature values, and that's going to be, let's pull this up again. Okay, x values right here. That's all of these. So right now we're going to be getting the x values for all of our curves here. So x values is temperature. And then for our y values, that's going to be the impact energy. Let me tuck that away right there. So y values, we have energy. All of the rows in the ith column. Okay, there we go. And then for x2, again, the x values, it's going to be our temperature. So let's do temp. All of the rows in the ith column, and then our y values now, that's going to be dBTT energy vec. dBTT energy vec. Okay, yeah, let's not unsuppress it yet. Or let's not suppress it yet, really I should have said. And here we go. So we already knew our y interception or intercepts from this, but our x-intercept values are right here. So they should usually just be one value, but it depends on how it kind of crosses the line. So you see For this one, we had 2, but it's actually just going to be a very first value. We can probably get a better visualization of that later as well. But yeah, the x-intercept values, that's our dBTT. So if we want to see this a bit better, let's just type in x-int. And there we go. We have, there's something else. Yeah, let's suppress this one. Okay. And here are all of our dBTT values. Again, taking the very first value if you see 2 of them. Okay, there we go. But we only have a transition temperature for the 2 steels. So right now we solved it for all 3 materials, but really we just need it for 2. Easier just to do it for all 3 because we're already in a loop. So those are the intersection points, and then I think we're done right now. And now we can just make our figures here. So we're going to be making the figure within our nested for loop because we want to make a figure for every single material for each sheet. Okay, so let's start this out. Let's call this plots. And I'm going to make subplots, so we have our left station and our right station. We're going to have 1 row, we're going to have 2 columns for these subplots. And this last argument is the position that it goes at. So my first pass in the nested for loop, that'll be in the first pane, so the very far left. Second pass will be the second pane, so very far right. Okay, let's plot this. We're going to do plot. X values, that's going to be our temperature. Y values, that'll be energy. Remember, I made vectors for those up here. I didn't have to, it's just, I don't know, I just did. Okay, and then we're gonna have a dashed line with our markers here. And we're gonna do line width of 2, just because I like that. And let's run this right now and we'll see our plots. Okay, so here's a 1 plot here. Yeah, okay. So we're going to get to you later on. I think yeah, maybe I need to have figure n. That's it. Okay, so we have our 2 plots here. This is for the second pass right now. And so we have our left station here and then our right station here. Okay, so I just remembered, as for the figures, both figures not showing up when we run our code, I think it was the same thing with the column lab. So basically, when we go through here, the first figure is being generated, but it's going to be like immediately overwritten by the second figure. But if we run our export graphics function, then it's going to export both of the figures. So anyways, just remember that. So for the x limits, so basically I already ran the code here, but there's some space on the right hand side and there's some space on the left hand side, and we want to take that out. So to that, we're going to use the xlim command. And here I have some things that are a little bit different than we've seen in the past. So I have xlim, that's going to be the minimum temperature. Then I have these empty brackets, and then I have all, and same thing over here. And basically that's going to run this, where it's going to look at basically the vector that we have, because we have a vector basically for the minimum temperature values, because we have 3 lines, and for the maximum temperature values, because we have 3 lines, or really 3 values. So it's going to work like that, and that's going to be how we constrain this in the end. If you didn't have these 2 arguments, then you would get an error in your code. So that's xlim. Let's add in our labels here. So x label, that's going to be temperature. Yeah, temperature. Oh yeah, we need our square bracket over here. And char 176 for degrees. Oh yeah, and then we need to have Fahrenheit. Run this, that'll update now. Let's put a space here. Okay. Yeah, it's fine. Okay. And then our Y label, that's going to be impact energy. Impact energy. And that'll be foot-pounds, rather. So foot-pounds. There we go. And then we'll put in our title. So remember, I made a a string array up top for the titles that we're going to have for left and right. So we have title. I just need to do titles of n. There we go, left and right stations. And then I'll say grid on, then I'll make a grid. And then hold on. So now I'm going to plot the energy transition line and the transition temperature lines as well. Okay, let me get this here. So the first one. Okay, yeah. So the first one is going to be our transition energy. So I'm going to do X line. That means we're going to have a line along the X domain. Okay. And for that, it's just X int. Remember, that's our transition temperature. So we have X int. And it's always going to be the very first value. So I'm going to put 1. And we're going to make this a black line. A black dotted line is what it should be. Jeez, I can't type right now. Black dotted line. And let's change this line width to 2. Now if we run it, there we go. We have our black dotted lines, and that is our transition temperature. And then we'll do Y line. This is going to be the energy transition line. So this was dBTT energy vec. Actually, we don't even need that. We could just, because, you know, X line and Y line, they're kind of different than regular plotting. So here, we can actually just do dBTT energy, and that's it. We can just have the one value, and that'll be okay. Because again, X line and Y line it's not the typical plotting that we have where we need X values and Y values. Okay, so dBTT energy, and we're going to make this a black dashed line with a line width of 2. There we go. And then we just need our legend now. So legend 1018 steel, that's the first one that we plotted. Then we have 4140 steel. Then we have 60 aluminum. And then we had our transition temperature. So I'm gonna write that as dBTT. And then we had our energy transition. And then let's put this location, what, the northeast, is that what I did? No, northwest, okay. Run it, there you go. Because I kept this open, do you see that, you know, because I kept it open, it generated new colors for the curves, but it did the kind of like first iteration of colors for the legend. So if I close out and I run it again, it should be synced up for the colors. And yeah, you see it is. Okay. Oh yeah, and then we have our graphics that we're going to export. So let's do that too. I'll type in get current axis, or type in what we want to call it. I'll call this vid graphs. We'll just keep it in here. You know, actually, because they're subplots, I think it exports differently. Yeah, you can see it keeps going through it all. So yeah, okay, so it didn't save right because I have subplots. Whatever, I'm not gonna go through that part right now. When you have subplots and use the export graphics command, that behaves a little weird. So you need to have some different code, and I haven't written that code in a long time, so I don't know what it is on the top of my head. Anyways, that is the video. Oops. So we solved for everything that we needed to. We used the nested for loop, and hopefully the explanations that I had for the dBTT, it was a little more in depth, or hopefully just understand that part a bit better. So that's the code for this lab. You know, in the end, it's not that much code. We only have, you know, like 56 lines of code. I could delete all of the empty lines, whatever. It's not that much. But that's because we used looping. So if you were doing it line by line without loops, yeah, I'm sure your code would be a lot more. Because you're doing the same thing just over and over and over again. So yeah, use loops when you can, because it definitely helps save on time. Okay, so that's it for this video. I'm not making one for the 6th lab unless people ask me, you know, after you turn it in, maybe you still want to see what I did, but that one's a really simple lab. It's really just plotting and calculating a few things. So there's nothing too tricky in that one. Alright, so that's it for this video. Bye bye, good luck on finals, see you later, or never, I don't know.